Alright, this will be your crash course into electricity and DC circuits, aiming to get you ready for Physics Olympics and to introduce you to these concepts that we'll then see later in the year. When we start off thinking about electricity, one of the really common metaphors we use is to compare an electrical circuit to a river. And in that analogy, the current, the electricity that's flowing, is the amount of water that we have in the river. Current in an electrical circuit is a lot like current in a river. The electrons are like the drops of water, and one stream of current or one stream of electricity is made up of many, many, many electrons or many, many, many drops of water. So electricity is simply equal to the flow of electrons, which you probably already knew. In order for there to be a flow of electrons, they have to have some place where they can flow, and that's what we call a circuit. And that's what we're going to talk about now. On page 731 in your Holt Physics book, you'll find a table that shows you the basic diagram symbols used in schematics. So the first one you should be familiar with is a wire, and this is just the path on which electricity flows through the circuit. It's given by a straight black line, and that line can bend or twist or go in any number of directions. But when you see a single line given in a schematic diagram, that's a wire. The next symbol you'll need to know, and this one's really important, is the symbol for a resistor. There are two symbols commonly used. The one that I've drawn here is the one that we'll be using. The next symbol you'll need to know is that for a bulb. If you notice that the symbol for a bulb looks a lot like a tiny resistor inside a globe, there's a reason for that. Light bulbs in a circuit create resistance. The symbol for plug is one that we will not be using in this brief unit because plugs are a feature of an AC circuit or an alternating current circuit. We'll only be dealing with direct current circuits, so no plugs for us. A symbol that we will use frequently is the symbol for a battery. This is a battery with a single cell, while this one is a battery that has multiple cells. This is the place where the electrons are going to flow from and return to. The symbol for a switch can be shown two ways. The first one shown here is in the open position, while the second one is in a closed position. When a switch is open in a circuit, electrons can't flow, and therefore there's no current flowing through the circuit. A switch is turned on when it's in the closed positions, and electrons can flow through the entire circuit. A capacitor, our final symbol, is a device for storing current, and a capacitor is actually a structure built out of two plates of material that are set parallel to one another. This is a standard capacitor notation, while this is one that can only be used on a direct circuit, and the polarity has to line up with the battery. You'll notice that the symbol for a capacitor bears some resemblance to a battery. Batteries store current, they store electrons or charge, so does a capacitor. This is a schematic of a very simplified direct current circuit. We have a battery located here, and charge will flow from the area of high potential to the area of low potential. Right now, however, no charge can flow because this switch is open. If we want charge to flow, we have to do something. That's better. Now charge can flow from the area of positive potential through that switch, because it's closed now, through the bulb, and back to the area of low potential, completing the circuit. The other part of the circuit that I hope you noticed is the light bulb. Why does the light bulb light up when charge flows through it? When current flows into the light bulb, remember that we said that that center part of the light bulb is a lot like a resistor. It's an area of high resistance to the flow of electrons within that piece of wire. Because it's got such high resistance, it generates heat, and you have heat and light coming off the light bulb. Hence, it glows. So the big primary thing to remember about circuits is any circuit, in order to work, must have a source of potential difference, and it must have a complete and continuous path back to the other side of that source of potential difference. Any circuit that doesn't have those elements will not conduct. Here's your first quiz question. Write it down on a sheet of paper. It's due when you walk in tomorrow. Which of the diagrams below shows a circuit that will conduct current? Okay, let's talk briefly about resistance. Resistance is just its opposition to the movement of charge through a material. You can think of it like friction inside a wire or inside some other material where current is attempting to flow. Any circuit, no matter what material it's made of, whether it's copper or gold or anything else, will have some native resistance. The wire itself will have some resistance. Materials which are very, very conductive, such as gold, have very low internal resistance. Things that are good insulators that are non-conductive have very high internal resistance. In addition, we can put a structure called a resistor within a circuit. That little tiny thing right there, that is a resistor. And they come in a lot of different sizes. This is a very small resistor and it has very low resistance. There are codes given by the bands on the resistor itself that tell you what its level of resistance is. When we create a circuit, we can put all kinds of resistors in it, and we can use different size resistors that have different levels of resistance to change the amount of current that's delivered to a specific device. There are two basic ways to wire resistors into a circuit. The first is in series, and in two resistors wired in series, current has to pass through one resistor, then the other resistor, before it can complete the circuit. The other way to wire resistors into a circuit is known as wiring them in parallel. When resistors are wired in parallel, current has two paths to travel, and so the current that goes through this resistor will not travel through that resistor. Okay, here's your next question. Of these four circuits, identify which ones have resistors only in series, which ones have resistors only in parallel, and in which ones the resistors are wired in both series and parallel. Resistance R is measured in ohms. That's handy if we ever want to be able to do any dimensional analysis, but it's also important as we start to talk about how to calculate the equivalent resistance of multiple resistors in a circuit. First, we'll look at resistors in series. These are easy because the equivalent resistance of the two resistors together is equal to the resistance of one plus the resistance of the second, and we could go on and on and on with as many resistors as you wanted to wire in. Resistors in parallel are really no more difficult, but they're a little bit trickier because you can't solve for the equivalent resistance. You can only solve the reciprocal of the equivalent resistance, which is given by 1 over the first resistance plus 1 over the second resistance, and on and on and on with as many resistors as we care to wire in. That's where we'll stop with these ideas. Tomorrow in class, we'll be working out equivalent resistance on circuits with parallel and series resistors. See you then.